Section 2.8 is the definition of the derivative. We are going to take our approach to derivatives a step further. Doesn't necessarily mean more difficult. It's just the next progression, if you will. And so, if you remember, we left off in section 2.7 with this formula here for the derivative. F prime of a equals the limit as h approaches 0, f of a plus h minus f of a all over h. So if we'd like to know the slope of the tangent line, which we also refer to as sometimes as the instantaneous rate of change, or even some other times as the instantaneous velocity at a for the function f of x, we would use this formula here. We learned that a simpler function previous to this, but this is where we left off. Okay. And yeah, the derivative of f of x at a. So what's the next level? What are we going to do here in 2.8? All right, so we noticed, and you may have even seen it before I pointed it out in that last section. This portion here sure looks an awful lot like the difference quotient, right? The only difference, the difference quotient has x's, f of x plus h minus f of x, but all the rest is the same. Okay, well, that is really just the very next step. So let me explain. So here's the definition of the derivative. Can slide this up a little bit. Okay. Oh, sorry, lost focus there. Okay. The definition of the derivative is exactly that. Let me make that a little bit darker. Instead of the a, we simply put an x in those three positions. So now it's f prime of x equals the limit as h approaches 0, f of x plus h minus f of x all over h. And there we have it, the difference quotient exactly as we know it. We throw a limit as h, our denominator, approaches 0, and that gives us off the full picture, what we're going to call as the definition of the derivative. So what's the difference between this and that previous formula? Okay. Here, notice we're not saying this is the derivative at any particular x value. This is the derivative for any x value in the function. So we'll really see what that means as we go through some examples. You'll get a concrete picture of that with different functions, specific functions. Just the idea here, if we can find f prime of x, then that acts like a function. We can then plug in a number and we'll be able to see what the derivative is right at that value. So what we'll do is we'll do a bunch of work here in general for any x value, and that will give us what's going to look like, just any old function that we're already familiar with, maybe a polynomial or something. And then we can plug in x values into that, after we've simplified this guy, and we'll know the slope of the tangent line or instantaneous rate of change, or however we want to think of it. And we can do that for several different x values. We won't have to walk through this limit process anew every time. Okay, let's move on. If that makes sense, great. If it doesn't, hey, we're about to see some examples. Well, what are we going to do? Let me keep that on the screen, that formula. Find the derivative function. Okay, so there we're talking about f prime x. Let's begin with a familiar example. This is what we saw back in 2.7 when we started off. F of x equals x squared plus 2x minus 1. If you remember, we found f prime of 3 for this function, but now we're going to find f prime x. Okay, well, we need to set up the difference quotient. We need to then, for this function, we then need to simplify the difference quotient. And then once we have that simplified, then our last step will be to perform that limit as h approaches 0, which of course is going to be as simple as just plugging 0 in once we have it all simplified. So let's go through that step by step. For this function, let's figure out that first part, the most difficult part, f of x plus h. Oh, looks like I've copied the I copied the formula because all right. Let's find that f of x plus h. X plus h squared, quantity squared, plus 2 times quantity x plus h minus 1. And if we FOIL that out, expand, that's a square. Okay, we get to this. Now we've done this several times at this point, so hopefully you feel pretty good about that. All right, we're going to take that, plug it back in. We are also going to plug in the original function here. Be sure to use parentheses. Here it is. Take a moment to write that, maybe pause the video, whatever you need to do. So we have f prime of x equals the limit as h approaches 0. There's our f of x plus h minus, be sure to use parentheses here, f of x, because that negative sign needs to distribute, and the whole thing is over h, of course. All right, pretty exciting. Once we have the difference quotient set up, we're going to simplify, and you notice lots of nice things cancel. It's always the case. With the difference quotient, you get some great cancellation, and, okay, yeah, x squared cancel. 2x minus 2x, negative 1 minus negative 1, that all goes away. And we are brought to this. So we're just simplifying in there. Very nice. F prime of x equals the limit as h approaches 0, 2x h plus h squared plus 2h all over h. Of course, what are we going to do now? Factor an h out of the numerator. That will cancel out. And at this point, we are safe to plug in that last remaining h to be 0, and we're going to have our answer. F prime of x equals 2x plus 2 after we perform that limit. Okay. Hey, let's kind of just pause before we go to part B of these examples. Let's pause here and reflect. So as you can see, our derivative looks like any, ordinary function that we're familiar with, 2x plus 2. So what if we wanted to know f prime 3? Right, this is the value we found back in 2.7. Well, if we want to know f prime 3, we're just going to plug 3 in. F prime 3 would equal 2 times 3 plus 2, and that would give us 8. Hey, that's the answer we got before. Wow, okay. So, yep, if I plug 3 in, they should agree, right? And they do. I still get 8. But now that I have the derivative as a function, f prime x, I could then immediately say, hey, what about any other x value? What is f prime negative 7? And it's just as easy as plugging it straight on in. F prime negative 7 would be 2 times negative 7 plus 2, which would end up being negative 12. So I know the slope of the tangent line at negative 7. And I can do as many as I want. I don't have to repeat that whole limit process if I get the derivative as a function of x. Hey, why stop here? There's an interesting one. How about f prime negative 1? Why is that interesting? Well, what happens when you plug negative 1 in? 2 times negative 1 plus 2 would be 0. maybe that's not a big deal, even after you see that. Well, I decided to give just a rough sketch here of the original function. This is f of x. Is that x squared plus 2x minus 1, right? If you graph the original function, we should see the values of these derivatives. So at 3, right, if we were to think of the tangent line there at 3, we did this before. Kind of difficult to draw by hand, but we know, hey, that has a slope of 8, right? That's what we discovered just a moment ago. Hey, what about, so that's the point at 3. Hey, what about the point at -1? Turns out that's the vertex of that parabola. So if you were to draw the tangent line, if it's down here at the bottom, the tangent line would need to be horizontal. Well, what's the slope of that horizontal line? 0. 0. And, oh, that's interesting. So this is actually a concept. It's good to just kind of get a glimpse of it at this point, kind of connect the dots and see it a little bit deeper, like confirm, draw it back to something we're familiar with. We're going to get really into this. Is going to be a crucial idea a couple chapters down the road, because look at what we just did. If we could identify where the derivative equals 0, that tells us where that vertex is on the parabola, right? Okay, so just kind of hold on to that thought. We'll come back to that later. All right, I'd like to do part B here in this video as well. So let's do something a little bit harder. Part B, we're going to look at h of x equals the square root of x to the third. Okay, so we see that square root, and if if we're thinking about a difference quotient and how to simplify that, right, a square root is going to need a conjugate, right? Okay, so that's going to come into play here. All those things we've been practicing are paying off. All right, let's go for it. Using the definition of the derivative, I'm just going to go for it and set this one up. We can sort of just dive in here. H prime of x will equal the limit as h approaches 0. Square root x plus h to the third. All right, well, there's, h of x plus h. Minus the square root of x to the third, the original function, all over h. Okay, there's the setup. Hopefully we all feel pretty good about that at this point. So how do we simplify? Well, it's the conjugate. So I'm just going to put that out here. We're going to multiply top and bottom by this conjugate of that numerator. Okay, like so. And a little bit different maybe than some examples we've seen because we got that cube inside. But really, I mean, it's not going to change a whole lot about what we do. Here it is multiplied out. So square root times square root, that's going to cancel, give us x plus h to the third. The middle terms cancel out. And then this times this, well, that's minus x to the third. Square root cancels there as well. And same strategy for the denominator. Don't actually distribute. Just say h times the quantity of your conjugate. Okay. And, just copying everything else. H prime x here, the limit as h approaches 0. We'll deal with this at the very end. All right, simplifying well. What's going to happen? We need to expand x plus h to the third. Okay, if we want to keep going. I will let you guys try that out maybe by hand. I'm just going to tell you what it works out to be. I know you could check this if you wanted to. I'd rather not spend a couple minutes or a minute even expanding that because we all get it. So here it is. Expanding x plus h to the third would give you x to the third plus 3x squared h plus 3xh squared plus h to the third. And you please feel free to verify that to yourself on some scratch paper. Then we're going to subtract x to the third, and we've got our denominator the same, and of course we're copying all these things as well. All right. So to continue simplifying from there, we will cancel out the x to the thirds, and we're going to want to cancel this h. So after these are gone, let's factor out an h, and we're just going to, we've almost got it now. Factoring the h leaves us 3x squared plus 3xh plus h squared, and of course h's cancel. Once we have the h canceled, then all we got to do is actually take this limit, plug in the 0 for the h's. Well, if it goes in there and there, these are just wiped out. Okay, and the 0 in here, well, what's that going to do? If the 0 goes in there, all I have is x to the third. So my denominator is square root x to the third plus square root x to the third. And this is my final answer. H prime of x. Oh, I see I did something. I wrote the limit again. I should not have done that. Because we just did the limit when we plugged the 0 in. Oh, man. Okay, so plugging in the 0 means we performed it. That's gone. 3x squared over 2 square root x to the third. Since once the 0 goes in, we've got that twice. Okay. And that works as a final answer. Very nice. Some of you may recognize, hey, this could be simplified. Okay, so to speak to that, because we have the square root and the x cubed, I am perfectly okay with this as a final answer, say on a quiz or a test. But you may notice we could write this even simpler. How is that? Let's break it down. We've got the 3x squared over 2 square root x to the third. Square root x to the third, isn't that x to the 3 over 2? If we thought of it just as a fractional power, a rational exponent, we call them. And then we could reduce the x's, right? 2 minus 3 over 2. Now I still have this 3 and 2, a lot of 3's and 2's going on. I still have these, so they will make the fraction 3 over 2. When I subtract there, I get 1/2. And you may know that x to the 1/2 is the same as the square root of x. So actually either of these two would be very nice final answers as well, and a little bit simpler than what's here. So you might answer this in either way. H prime x equals 3 over 2 x to the 1/2, that works. Or h prime x equals 3 over 2 times the square root of x, simpler versions of that same derivative function. Okay, very nice. We have the answer 3 times actually. Before we stop this video, I'd like to just reflect here on what's going on. And I think it'll be actually clearest with this final version of the simplification there, 3 over 2 square root x. I'd like to look at the domain. Just think about the domain of the original function and the domain of the derivative. So since it's well off the screen now, although hopefully you wrote it, what is the domain of that original function h of x, right? It was the square root of x to the third. Well, I have it written here already. The domain is from 0 to infinity. 0 is okay, but we cannot allow negative numbers, right? Because that would give us the square root of a negative, and we don't deal with imaginaries in calculus, if you didn't know that already. So the domain, the real number domain, from 0 to infinity, right? Take a look at that last version of h prime. What's the domain of h prime? And it matches, because that would be from 0 to infinity as well. So it's not a surprise that when we perform our derivative, values of x that were not allowed in the original are not allowed in the derivative either. Makes sense. Okay, so we're going to go a bit further with this idea of the domain in some examples coming up, and there's a point to all that. There's a theorem we eventually get to with it. Okay, we're going to stop this video here. See you in the next one.